So when we go through and we start solving some of these problems, we're still kind of looking at there's a couple different choices. Is it just how much work is done type of problem? Is it how much power, or is it a two location? So those are kind of the parameters we're working in, and sometimes it's a two location with work in and work done by friction and. So we're going to take a look at the first problem on the worksheet called in-class lack of conservation, and I didn't number them, but we're going to look at the first one. So it says a 7 kilogram crate is accelerated horizontally from rest by a 40 Newton force for a distance of 2.5 meters. What is the final velocity? So, quick sketch should hopefully help. We can do that, right? No? I was pretending. So we have a 7 kilogram object that is being accelerated by horizontally from rest by a 40 Newton force. So the force is an applied force, and it's being applied horizontally. Now, technically, yeah, there is a gravitational force and there is a normal force, but we don't really need those right now. If we need to, we can come back to those, but we don't really need them. And it says that it moves a distance, it accelerates it for a distance of 2.5 meters. So the fact that it's accelerating it means it's moving in the same direction. So this is a two location problem. It's starting, say, like right here, so this is location 1 on my little, and it moved 2.5 meters. This is location 1. And over here is location 2. The question being asked is how fast is it moving at location 2, essentially? It's a horizontal surface. So because it's a two location problem, we're looking for V's, we're looking for H's, we're looking for spring stuff. There's zero mention of a spring, so I'm not even going to worry about the spring stuff. Because it's a two location problem, we're looking for things with PEG, with PEE, and with KE stuff, just like we did right before break, two location problems. We just had this special type that was called conservation mechanical energy. So because it's a two location problem, the equation we use is work in plus work done by friction is equal to our change in mechanical energy. Now if work in is 0 and if work done by friction is 0, then we could say ME1 is equal to ME2. However, that's not the case. Now there's no mention of friction. I was looking at this problem a little bit ago. I probably should have clarified and said like a frictionless surface. It should have probably said a frictionless surface. It didn't mention anything about friction. But to kind of start up here in this, there is no mention of friction, so it's a frictionless surface again. Probably should be more like direct with that. And the other thing is there work in? And when we look for work in, the question we kind of ask ourselves is there an applied force with the displacement? And because the answer is yes, there's an applied force, and yes, the object moves, there's going to be some work in. So because there is work in, it's not an ME1 equals ME2 problem. We're going to have to use it in this long form. So what I like to do is I like to go through and I like to expand this equation out before we get too far. And say work in is equal to my change in mechanical energy. And important that we put the second location first, so it's NE2 minus NE1. The order is important. It has to be final minus initial. If we take ME2 and we expand that out, I'm going to put brackets around it. ME2 is what we get when we take our PEG at location 2 and we add it to our PEE at location 2 and we add it to our KE2 at location 2. That's my ME2. And then it's minus bracket my ME1, which is my PEG1 plus my PEE1 plus my KE1. That's about as expanded out as we can get here. Now I guess we could have kept it, work done by friction in there, but we took care of that already. We go through it, we ask ourselves the same questions that we had earlier with these. Is there a height? Is there a compressed spring? Is it moving? So that's why on my picture, I put those things in there. And if we go through and we kind of label this, it kind of hopefully will force us to think about this. If it's talking about moving across a horizontal surface, if it's horizontal, it's flat. So what's my H1 and what's my H2? Yeah, 0. So because it's horizontal, my H1 and H2 are the same value, and works out pretty nice if we just say the value of that is 0. What's our V1? What is this, how fast does this object go initially moving? 0, right? Because it says from rest. So my V1 is going to be 0. There's nothing about a spring, so I didn't even write spring stuff there. We could potentially add that. So then we kind of go through and we say at location 2, is there a height? And we said no. At location 2, is there a spring? Which we said no. At location 2, is it moving? Yeah, I just don't know how fast yet. Then at location 1, is there a height? We said my H was 0. We said there was no spring. And for KE, is it moving? We said it started at rest. So what was a pretty long equation to start with ends up simplifying quite a bit in this particular problem. I personally like to kind of go through and keep working as it is, and then kind of go through and instead of saying KE, it's 1/2 mv2 squared, and we don't really need it, but it is technically a minus of 0, but we don't really need to subtract at 0 because it's going to be. So what we're solving for in this problem is right here. There's one more thing we need to determine before I plug numbers in, and it's that work in number. If we wanted to, we could substitute and we could put that equation in. I don't know why. I just kind of like to keep work in and work done by friction separate if possible. Sometimes I put it in there, but I generally kind of calculate it first, then put a value in. So our work in equation is plus or minus our applied force times the displacement. So, work in is equal to plus or minus. If my applied force is in the same direction as my displacement, it's going to be the plus. If my displacement and my applied force are in opposite directions, then we have to choose the minus. I drew my picture with an applied force arrow to the right, and that force accelerates the object, which means it's going to make it start to move. So they're going to be in the same direction. So that's going to be a plus. And then we take our applied force of 40 times the displacement of 2.5. Work in ends up having 100 joules, and it's a positive 100 joules. What that's saying is 100, positive 100, is it's adding, plus, it's adding 100 joules worth of energy to the system. Now, if we kind of look back to this line right here, where we crossed a bunch of stuff out, if we talk about how much mechanical energy it started with, how much ME1 does it have? It had no mechanical energy. It starts with 0 mechanical energy. But it gains energy, and the last type of energy the only one we have left is kinetic. It gains kinetic energy. And why does it gain kinetic energy? Because I push it over some distance. So now it's kind of just at the point where we plug numbers in and we solve, and we say positive 100 is equal to 1/2 our mass of 7 V2 squared. 100 is equal to 3.5 V2 squared. Divide both sides by 3.5, and then take the square root. Maybe I did that all in one step. I don't remember now. I must say, yeah. So divide both sides by 3.5, and we get 28.57 V2 squared. And then you take the square root to get a final answer of V2 of 5.35 meters per second. It's a 2-location problem. There was some work in. There was no work done by friction. And we had to solve for final velocity. Now, we could do slightly different things with this long equation. If we were given the final velocity, we could solve for work in. Given the final velocity, we could solve for the work in, which then could get us the applied force. If we were given a time, or we somehow calculated a time using a Fab 5, we could calculate power. That's another option. Before we switch pieces of paper, questions on that one I can answer. Like I said, it probably should have been more specific and said that it was frictionless. Okay, then yesterday. 19, I think. Yeah, number 19. I want to go through this calculation, number 21. Number 21 is very similar to a lab that we're going to do tomorrow in class. It's a 2-location problem, but we're solving for something a little bit different. Big picture is we're going to solve for power. So what this is, and I looked this up, I think it was originally in like a textbook, and then I did a little research. So every year there's this, at least there was, a race at what used to be called the Sears Tower, is now called the Willis Tower in Chicago. And you race to the sky deck, which is this observation thing that you look out at. And there's a race. And in 2009, there was a guy by the name of Matthias Jahn, I don't know how you would pronounce his name, from Germany, and he set a world record of that climb. And he climbed to the top of the Willis Tower in 13 minutes and 9 seconds. So what we're going to try to do, ultimately, the ultimate thing we're trying to figure out is how much power did he produce by climbing this series of steps. There's some information that we need to know. We need to know how high did he climb. It's a two-location problem, so he's going to start on the ground floor. He's going to go up to the sky deck. It's a two-location, so we got to know the height here. We got to know the height here. We got to know how fast he's moving here. We got to know how fast he's moving here. We got to know some spring stuff, which there's no spring. And if there's friction, if you applied a force, which obviously if you're climbing a flight of stairs, you are applying some force to kind of climb the flight of stairs. Now, we're going to gain height, so we're going to gain PEG. So in order to know, or to calculate PEG is m times g times h. We need to know his mass. And to determine kinetic energy is v1/2 m v squared, so we'd have to know his velocity. Okay? So those are some things that we have to do. So I did a little research. There are 2,109 steps to get to the top of the sky deck. Each step is 0.195 meters tall. And it took them 13 minutes and 9 seconds, which I did the conversion because we're going to use seconds. 789 seconds. It had to know his mass, which is kind of a weird thing. So Matthias is a real person, and I actually emailed. Matthias has a website, and there was a contact me button. So I clicked that, and I said, hey, I'm just trying to calculate your world record climbing attempt of the world Willis Tower. We're trying to determine your power output in a class. Would you be so kind as to share how much you weigh? And this is like a couple of years after the fact. And he replied, I saved the email, and he said something, blah, blah, blah. At the time, I was 63 kilograms, so that's his, according to him, that was his mass when he actually did this. And then he said, regards, Matthias. We're like best bud pretty much now. Oh, by the way, he prefers right-handed turns, according to his website. He prefers to put his hand and turn this way up the stairs, not this way. I don't know if he's still doing it. I kind of quit following him. His website was kind of blank for a while. Yeah, it's kind of creepy. I know. It's for science. It was for a class. It's not as bad then. But the idea is we can go through and we can calculate how much power someone produces when they climb a flight of stairs, which you are going to climb a flight of stairs tomorrow, and you're going to have to calculate how much power it takes you to climb that flight of stairs. So this is pretty similar to the calculation you do. So the idea is, he starts here. That was supposed to be a headband, I'm assuming he wears a headband. And he's going to climb a bunch of stairs, which then at some point, these stairs go like this, and they go back and forth, and ultimately, he's going to end up here. Now, the way this was actually originally written was, I gave you the total height, but I decided not to do that because tomorrow, you aren't going to know the total height. You're going to know the height of a step. So each step is 1.95 meters. Now, you, don't worry, are not going to climb 2,109 steps tomorrow. You're only going to climb about 30? I don't even remember how many there are. We'll have to count them tomorrow. But the idea is this is location 1. This is location number 2. Big picture here is we're calculating the power. And power is work divided by time. Work, time. Time, pretty easy. You use a stopwatch. And that was, we have that as 789 seconds. So there's 2 ways we can find work. We could look at work in is equal to, I'm going to erase this in a second for the record, is equal to plus or minus our applied force times our displacement. Now, he's going up, so it would be a delta y. The potential problem with this is I don't know what the applied force is. So that option, not the best option. We do, however, if it's a 2-location problem, we can solve for any equation or any variable within this equation, including the working. So in our power equation, work is divided by time. We're going to calculate work using the long equation, which then we can plug into our power formula. So because it's a 2-location problem, things we're looking for velocities, we're looking for heights, we're looking for spring stuff at each location. If he starts on the ground floor, would be a pretty kind of good choice to choose his H1 to be. Seems pretty logical that we choose his H1 to be 0. And how would we go about calculating his total height? If I know one step is 0.195 meters, if I go up 2 steps, I add 0.195 to 0.195, so that gives me the height of 2. And I could do that for 3 and 4 and 5, but remember there's 2,109 of them. So if you know the height of 1, and assuming that all the steps are uniform in height, I can take the number of steps, 2,109, and if I multiply the height of one stair, that will get us the total height that Matthias climbed. 2,109, yep. 2,109 times 0.1, 2,100, 0.195. So Matthias climbs a total of 411.255 meters. It's a little bit more than once around the track. He goes straight up, is what that ends up being. Right, track is 400 meters. So we now know our H1 and we know our H2. Now this is a race, so if you are going to get timed in a race, how fast are you allowed to be moving prior to the start of a race? 0. And if we're talking about his velocity going up, once you get to that top step, how fast are you going up once you're at the top? 0, right? You get to the top, and like, yeah, I made it. Probably like fall over in the process, but that's maybe what this world-class athlete does. Okay, so we start on the bottom at 0 meters per second, because that'd be a false start otherwise. And once we get to the top, we can't go up anymore, so our velocity at the top is also going to equal 0. Friction, yeah, there's a little bit, but we're really talking about air resistance of you going up. And we're not talking about how far did they go this way. I'm really just looking at vertical height gained. So when we look at this long equation, we can say, well, there really wasn't any work done by friction in this problem. A little bit of air resistance, probably not going to slow them down too much. So we expand this work in equation to be our change in mechanical energy, which is ME2 minus ME1. I would encourage you not to get lazy on this part. And sometimes people are like, I'm just going to write the ones. I would really encourage you to write all of the types of energies out and then cancel them one by one after you kind of think about whether that type of energy is there. So ME2 is PEG2 plus PEE2 plus KE2 minus, important, minus bracket PEG1, PEE1, KE1. All three of those also added again, the goal, our partway goal is determine the work in, because we're ultimately trying to calculate power, and we need to know the work, and we can get to work by solving for work here. So, for height, is there a height? For a potential elastic, is there a compressed spring? For KE, is it moving? And we ask ourselves those three questions at both locations. And yes, we have a height at location 2. There was no spring at location 2. We said that once you get to the top of the steps, you stop moving upwards. At the bottom, there was no height, there was no compressed spring, and we said that'd be cheating if you were moving before we started timing. So this equation really simplifies down quite a bit to be our work in is equal to M times G times H. So we take his mass, which I emailed him about, 63. So we take his mass, 63, times gravitational acceleration, he's on Earth, so 9.8. And we went through and we said if each step is 1.195 meters and there's 2,109 of them, how high did he climb? It's 411.255 meters. And when we multiply those three numbers together, we get the work that Matthias put into climbing the stairs at the Willis Tower. 253,908,987. So 253,908.837. That's a lot, just for the record. But he climbed like 2,000 stairs. If we're ultimately trying to solve for power, then we can go through, and now that we know the work, we can say his power is equal to 253,908.837. And it took him 13 minutes and 9 seconds, which I just took 13 times 60 plus 9, to get 789 seconds, because it has to be in seconds. This has to be in joules. This has to be in seconds. So if you take more than a minute to climb the flight of stairs tomorrow, you'll have to convert that into seconds, but I think we'll be okay with that. So when we go through and we take 253,908.837 and we divide by 789 seconds, we get a power of 321.81 watts. Assuming I did all my calculations right. Sure. 9, 5. Yeah, I think I'm good. So that's 71. Now, part of tomorrow, not only am I going to ask you how many watts did you produce, I'm going to ask you how many horsepower. And that's just really a conversion factor. If you take your power, there's 700 and, I don't have it in front of me, there's 700 some watts per horsepower. So he only produced 300 some watts, so he's right around half a horsepower. You have to actually do the calculation. But it's just another conversion, is all it is. okay? So we can also use that long equation to calculate work. We can solve for velocities, we can solve for work. And if we use that work, and if we know time, we can then calculate power, which is what the goal of this was. And that's what the purpose of tomorrow's lab is going to be, for you to calculate how much power you produce when you climb a flight of stairs. So, I'm warning you, we're going to climb a flight of stairs tomorrow. We're going to go up the stairs once. It's up to you whether you run or walk. I have two basic rules. You hit a minimum, you got to walk at a normal pace. Can't see like how slow can I go. You just got to at least walk at a normal pace. And the second rule is you aren't allowed to fall and smash your teeth on the stairs. I just don't want to deal with that. It hasn't happened yet that I can remember. I've had a few trips, but no smashed face, so we've been good. So just be careful when you climb the steps. If you need to use the railing, feel free to use the railing. We're going to climb a flight of steps tomorrow. So maybe you need to change your footwear. I'm guessing you're probably going to be fine with whatever shoes you wear on any given day, because you probably climbed the stairs at least once throughout the school day. So we'll do it one more time. But just be aware that we're going to do that. The actual stair part only takes a short period of time. We'll go through the calculations as we go through. All right. I'm going to not go through another problem because you guys don't want to listen to me talk anymore. A worksheet that is called Work and Power Practice. Some of these problems I give you the work. Some of the problems I give you the applied force and the displacement. You have to calculate work. If it's a two-location problem, we're probably going to have to use that really long equation. If I ask you to calculate how much power, you're going to need a time, and I wasn't nice enough. I don't think I'm nice enough in any of these to give you the time. So in order to determine the time, you'd have to go through and do a Fab 5, and I even put hint Fab 5 problem. So you can get started on this. I don't have it put in Canvas quite yet. I'll probably have it by the end of the class. Between today, tomorrow, the lab tomorrow, that's kind of where we're going to be. Is we'll be finishing this worksheet tomorrow. We'll be doing the lab calculations tomorrow. So I have 2 stacks. Help yourself to one. I'll have it in Canvas. This will be a Canvas submission, but it is not due tonight. It'll be due tomorrow. So let me know what questions I can answer.